there's another thing I want to talk about. So we can get a uniform distribution, as I already mentioned. We get a large number, then we just divide it by a larger number, then we get a number between 0 and 1. But how can we get any distribution using this uniform distribution? For example, I have a distribution from 0 and 1. Then I want to create a normal distribution. How do I do it? Does anyone want to volunteer to talk about that? Anyone has any idea? Given you a uniform distribution, how do you produce any distribution you want? Actually, it's very easy using this inversion method. Let's suppose you want to create a normal distribution. Then you create the CDF of the normal distribution. And vertically, this number should not exceed 1 and it should not fall below 0. Then you vertically use a random number generator to select a point, for example this point. Then you find the point on the x-axis, this point. By using this method, you are going to get a distribution as you want. Why is that? Do you see the reason? Let me repeat that. You want to get this distribution, then you vertically using uniform distribution to get the number. And you go to the distribution curve, CDF curve, then you find the x. By doing this, you are going to get the axis in the distribution you want. I think I have to prove that, and it's very quick. So this is CDF. This is point A. This is point B. This is Y. This is X. Okay? So this I'm replicating this graph. What's the probability that you will get a number between A and B? You will be when you get a number between this, you also get two numbers between these, right? And the probability that you get numbers between these is equal to FB minus FA. We use F to indicate the CDF, right? So that satisfies the definition of CDF. Do you see that? This is FB, this is FA. If the probability that you get a number out of, between A and B is equal to the probability that you get a number using uniform distribution between FB and FA, which is equal to FB minus FA divided by 1, right? And this, according to the definition of CDF, it will be integral of A, B, then the original PDF, fx dx. So I think it's very straightforward, and if you don't understand, just spend some time on it if you want. Okay, let me repeat this. You have a uniform distribution, then you select a number, then you match this point from y to x. You get the x you get is following the distribution. This is called the inversion method. So we all agree that we can get any kind of non-uniform distribution based on uniform distribution. Now I have a quiz for you. Here is a PDF I created. It's a continuous PDF. And we have 2 points, A and B, between 0 and 1. All we know is PDF of A is half of the PDF of B. Okay? So this is PDF function. You can think it as a distribution function. So FA is half of FB. Okay? Okay. The first question is, we are going to get a number from this distribution, and we have two probabilities, x equal to A and x equal to B. Which is bigger? Can anyone answer that? Which is bigger? B is bigger? Which is bigger?
We can't tell.
They are both 0. For a continuous distribution, the probability that you are going to get a certain number is 0. So actually they are both zeros. If you want to draw the number out of a continuous distribution, you always get 0. Now we use LCG and the inversion method, and we create a PRNG following this distribution. And then we use X to indicate the output of PRNG. Then, for probabilities, Px equal to A and equal to B, which is bigger? Anyone? The only difference is this time, when simulating this distribution, we use a random number generator, and we use the inversion method. Then we generate numbers. So for the result equaling to A and the result equaling to B, which is bigger? Which one? Can anyone answer?
Would they be the same?
They won't be the same. Okay. I don't think any of you can answer this question. So this is actually a very complex problem. First of all, you have to understand that A and B may not be able to be represented in computer system. For example, this is a program to test it. I wrote a simple program. I assign this number to D1. I assign this number to D2. They have 1 digit difference. As you can see, this number is too long, so it cannot be fully stored in by a double type. And if we can compile it, and let's check the output. Let's check the source code, compile the source code. This is written in C#, and C# programs are compiled into an intermediate code. If we check the source code, intermediate code, we see that this is D1, this is D2. Actually, they are all truncated, right? So they are the same, actually. Okay, but this problem is not the biggest problem. Let's assume A and B are both able to be represented in computer. There are still chances that A and B will never be fetched. Because as we mentioned, in the linear congruential method, how do we get a distribution between 0 and 1? We divided that by n. So the result can be is from 0 to 1, but the interval will be equal to 1 over n. If we divided something by n, and this is any integer, then we get numbers equally and with equal intervals. The interval will be the inverse of n. If this is 0, this is 1, we are going to divide the space between 0 and 1 into a lot of segments. And now let's assume they can all be gotten by this distribution. Then the answer will be the probability of getting B is twice as high as getting A, because it's higher. Because now it becomes a discrete distribution. Are you following me? Okay, let me repeat. First, you cannot be sure that A and B can both be represented. If they can be presented, you are not sure that they can be presented by 1 over something, 1 over m. But even if they can both be represented, then B, probability of getting B, should be twice as high as probability of getting A. Okay, because now it becomes a discrete distribution. It's no longer continuous. Okay, clear? So let's go to the last part of this lecture, which is the PRNG applications in traffic simulators. Actually, I checked the traffic simulators we are using, and I examined what random number generators they are using. The first one is PRNG. PRNG gives you an option to use either Mersenne twister or another one called Mazzaglia, I guess. And I'm not sure if this one they mentioned is this multiply with carry, this code. I'm not sure of it. They only provided me with 2 options. But let me show you how you do that. In parameters, if you go to edit and call model attributes, you are going to see a lot of things. Here you can select the RNG type, either Marzaglia or Mersenne. Okay? Remember these. And you are going to set a seed here. So in a word, parameters provides you with 2 choices, Mersenne twister or Marzaglia. Then what about other things? In MSUM, it's unmentioned. I searched the menu, it's unmentioned. In recent, it's unmentioned. If they are unmentioned, we can assume they are linear concurrential. In Sumo, it's Mersenne twister. In Cosine, it's linear concurrential. And the parameters here are listed here. Their linear concurrential is very special because they have a zero number of seeds. Then let's go to transit. Transit is also using linear concurrential, and it has only 2 lines of code. So actually, I want to limit my analysis in the class of the program, because last time somebody told me that it was very difficult to understand a lot of code. So I will limit the size to only 2 lines. So here we have 2 lines to generate random numbers. And how do you tell it's linear concurrential? So R is the output of this generator, and R is equal to R multiplied by something plus something. So this will be A